All right, so to continue our discussion about forces, we talked about Newton's first law, and he has three laws of motion. That first law is the law of inertia, and that is a body at rest will stay at rest, and a body in motion will stay in motion until a net force acts upon it. Well, we've covered that. Now we need to move on to what Newton's second law is, because it relates to that first law. They all tie together, these three laws. So I have conveniently written up Newton's second law of motion for you. I want you to take a look at it here. The acceleration of an object by a net force, remember there's that net force thing again, is directly proportional to the magnitude of that net force in the same direction as that net force and inversely proportional to the mass of the object. That's a lot of words. And as a definition, this seems very cumbersome, but it's not really. And we're going to examine this step by step and talk about this conceptually and then quantify it mathematically. So let's look at this first part first. I've got to highlight some stuff. Take out some of the words, make it a little bit easier to grasp. So we're talking about acceleration is directly proportional. In other words, as one gets bigger, the other gets bigger. Or as one gets smaller, the other gets smaller. So the acceleration is directly proportional to the magnitude, and that's a fancy word for size, of the net force. So this is basically saying that the acceleration is bigger if the net force is bigger. The acceleration is smaller if the net force is smaller. And that kind of makes sense. If we consider a free body diagram here, box sitting on a surface, we've got a weight and a normal force, and they are in equilibrium, so we don't have any motion changing there. Let's say I have a frictional force working against you of 5 newtons. And then I apply a force of 5 newtons. Well, the motion is not going to change, but if I apply a force of 10 newtons, the box is going to accelerate in that direction. And we know that to be true already. Now, here's what Newton's second law states. It says that the acceleration, or how fast this thing is going to change its motion, how fast is it going to accelerate, is directly tied to how much net force there is, how big that net force is. Well, in this case, the net force is 5, and that force will cause an acceleration. But what if we provided a force of 50 newtons? Now think about this. I got more force going that way. The frictional force is still 5. Well, now I've got an even bigger net force. Well, a bigger net force is going to cause a much greater acceleration. That's the crux of Newton's second law. It basically says that the acceleration is proportional to the size of that net force. So the bigger this net force, the bigger the acceleration. And the flip is also true, that if I reduce the net force, if I have less net force pushing on the object, the acceleration isn't going to be as big. So let's look at Newton's second law in action. I'm going to take an object, a little toy truck here, and I'm going to put it on this ramp. And we understand how the forces are in play here. We've got a force, a parallel weight going down the ramp that is going to pull on this toy truck. It won't act to pull it down. Because it's on wheels, there's literally very little friction going on here. We know that the force pulling down the ramp is going to cause this truck to accelerate. Let it go. There it goes. You can see it was speeding up as it went down the ramp. There was a net force pulling this way, and it accelerated the toy truck down the ramp. Now, how can we make the force bigger? Well, if we make the ramp steeper, we know that mg sine of theta, that parallel force, that parallel weight, is now bigger. Well, the force is bigger. What am I going to see different here? I'm going to see a greater acceleration. And it's really easy to see that. You saw that that truck accelerates a lot more when the ramp is up higher and that force is greater. Gets even higher, and you know what's going to happen. You're going to see a much greater acceleration because we're making the force bigger, so the acceleration is going to be bigger. Like that. All right, so we get that first part taken care of, underlined in the red. Now let's examine this part in the green. The same direction as the net force. So all this is saying is that the object is going to accelerate in whichever direction the net force is operating. Because remember, acceleration is a vector. It has a direction associated with it. So in the case of my ramp, in the toy truck, I could see that there's more of a force going down the ramp than there was going against it. This parallel weight was greater than the friction up here. So which way is the truck going to accelerate? Down the ramp, because that's the bigger force in play here. When the ramp was horizontal, it doesn't accelerate at all. A, because there is no net force, hence there's going to be no acceleration. So now this is starting to look a little bit easier. This is saying that the greater the net force, the greater the acceleration, and it is going to accelerate in whichever direction that net force is going. Consider the truck like this. We have a weight force pulling down, and I am applying a force to hold it up. Right now the forces are balanced and the motion is not changing. If I release my applied force and then the weight force is the only one acting on it, that becomes the net force because there are no others. It is going to accelerate in the direction of that net force. In this case, the weight always acts down. And we know this to be the case. It's going to accelerate downward. Not a very difficult concept. Seems a little wordy in the definition, but it kind of makes sense. It's going to accelerate in whichever direction the strongest or the net of all the forces is operating. Finally, this last little part here. Going back to acceleration is inversely proportional to the mass. Inversely means opposite. So as one gets bigger, the other gets smaller and vice versa. So let's look at this object here. Take my truck again, and I'm going to apply a net force. Right now there isn't one. I'm going to give it a little bit of a push. And I see the truck accelerated that direction. Well, this truck's pretty light, a whole lot of mass to it. If I put the brick, now I got a lot more mass to this truck here. Surfaces are the same. Everything else is the same. The only thing is now I got a more massive truck, and I'm going to apply the same amount of force I did to the empty truck. And it didn't hardly move at all. It accelerated a little bit. But this goes to show you that the mass, the force, and the acceleration are all related. That if I want to accelerate this more massive toy truck, I have to give it more force. Something that isn't very massive doesn't need much force to get it to accelerate. But if it has a lot of mass, I'm going to need a lot more force to accelerate it. Now, think about this. Same force, acceleration was lower. Same force, acceleration was higher. So there we see that inverse relationship. As the mass got higher, the acceleration got lower. That's what this says. This says basically the acceleration is opposite the mass. So if the mass is greater, given the same force, the acceleration is going to be lower. So here's kind of the final summation of Newton's second law. Yeah, all those words are important, and the relationships are very definitely true and important. But Newton's second law can be expressed mathematically with a formula. And that's the final piece here. Newton's second law is basically that. Force equals mass times acceleration. The greater the force, the more push you give. Provided the object is the same, the greater the acceleration will be. If I gave the same amount of force, but the mass becomes bigger, that means that number is then going to be smaller to make the same quantity. So this has all of the words of Newton's second law kind of tied up in a nice little neat formula. And we will now do some math problems where we play with some numbers and we'll see those relationships that match the words we had in that nice lengthy definition of Newton's second law. So at this time, I want to turn you loose, get you started on the forces homework problems that are Newton's second law, and start applying this information.